Hi, so today we're going to talk about how Facebook brought QUIC to billions. Next slide. So first off, who are we? So my name is Matt Joras. I'm a software engineer on the traffic protocols team at Facebook. I'm also one of the co-chairs of the ITF QUIC working group, which is the group that standardized QUIC.
And my name is Yang. I'm also a software engineer on the traffic protocols team at Facebook.
So what is QUIC? To be really brief about it, QUIC is the next internet transport protocol. Next slide. So in terms of the more traditional OSI layering model that everyone's probably familiar with, you have application, security, and transport layers. So at the very top, you have HTTP semantics. These are things like get, post, other things like that that form the basis of HTTP requests. So under that is the mapping of those semantics to an actual protocol. So the one that's existed for a while now is HTTP2, and as you might expect, HTTP3 being 3 is the next version and is QUIC specific. Both of these provide things like prioritization and header compression, and in HTTP2 it provides the stream multiplexing. So the next layer is the security layer. Now this is where things start to diverge a little bit. With the traditional stack with HTTP2, underneath it is usually TLS, and usually TLS 1.3. So TLS provides things like authentication, decryption, and generally makes the transport secure for use on the internet. Now on the QUIC side, you notice that there's not really a clean delineation, and this is because TLS is sort of baked into QUIC. Then what that means is there's only one handshake. There's not like a separate TLS handshake and QUIC handshake. There's just the QUIC handshake. And also the encryption is done on a per packet basis. So then when we go into the transport layer, again, we see that there's a bit of a difference. So on the left-hand side, we have TCP, which everyone's familiar with. It's connection-oriented, provides reliability on the internet, provides congestion control, things like that. And also, of course, provides the typical TCP byte stream semantic, which is usually exposed from something like a socket. Now, QUIC has some of the same things. So it has things like congestion control, reliability, has connection-oriented behaviors. But what's different is that it has stream multiplexing. And what this means is that QUIC exposes multiple independent streams on a single connection. And they're independent insofar as one stream does not block the delivery of another stream. And this is a fundamental difference with TCP that you can only achieve with multiple TCP connections. Additionally, we see another difference, which is that QUIC has UDP underneath. And why is this? Well, TCP was defined a long time ago and had the luxury of being its own separate internet protocol and getting its own internet protocol number. This isn't realistic to do anymore because it's hard to update old equipment to understand new internet protocols. So instead, QUIC basically piggybacks on top of UDP like a lot of other protocols do, and that allows it to transit around the internet unperturbed. And of course, both of these sit on top of IPv4 and IPv6, which is just the way that we route data around the internet. Next slide. So why QUIC? We already kind of touched on a little bit this, but one of the biggest reasons is something that we call ossification in protocol design. And ossification is a word to me that means to become bone. And what that's referring to is that protocols like TCP have existed for so long and their wire formats are so well known that it gets really hard to change them. And that's because there's a lot of equipment on the internet that makes assumptions about that wire format and may do things like drop it or modify it if it diverts from its expectations. QUIC solves this by encrypting the vast majority of the protocols. So there's not really much exposed, which means that we can change whatever goes on underneath the encryption because no one can make any assumptions about it. Another key advantage of QUIC is since it's built on top of UDP, that allows us to implement it in user space. And this is important because TCP is generally implemented by your operating system and is kind of untouchable and unchangeable. Like it will change slowly over time, but you don't have much control over it. It's hard to iterate on it or extend it or modify it and then experiment with those modifications. With QUIC, since it's implemented in user space, we can change and iterate it as fast as we can push software to our servers or release software to things like mobile apps. And of course, additionally, as I said before, QUIC has independent streams that can be multiplexed at the connection layer. And since it's been designed recently, it can integrate decades of experience running protocols on the internet like TCP, which lets us have state-of-the-art loss recovery. Next slide. So let's talk about QUIC at Facebook. So we have the diagram, same diagram we saw earlier on the left, and this is how our software fits into it. And all of these are pieces of open source software. So the top three are Proxygen, Fizz, and MoveFast. And they together are C++ implementations of HTTP, TLS 1.3, and the QUIC transport protocol. And all three of these taken together are how we implement our servers, so our web servers, our load balancers, things like that. And it's also been packaged together and with what we use in the mobile apps to implement basically a networking stack. And this is really valuable because we can share code from on the client and the server and iterate it on as fast as we can release apps and as fast as we can release servers, software to our servers. And the bottom one is the one that's a little bit of an odd one out, but it's our L4 layer 4 load balancing software called Catron, which is based on XDP and eBPF, and it allows us to load balance both TCP and QUIC connections consistently and reliably for our data centers. Next slide. So all that sounds great, right? We have this new modern transport protocol. It's encrypted. Everything's great about it. We have all this software that we implemented, and so we probably just implemented it, turned it on, and everything was great. Next slide. Obviously, though, that's not really how it happens. And so to talk more about that, I'm going to pass it over to Yang.
Thank you, Matt. Yes, so it turns out changing the transport layer protocol and HTTP at the scale of Facebook is actually quite challenging. Before we dive into some of the interesting problems we solved in the past couple of years, let's first look at how exactly the networking stack looks like in Facebook and Instagram app before we start to do this transition into QUIC. So they were both using TLS 1.3 with early data enabled. On the Facebook side, all the API requests, aka GraphQL, and all the static requests, whether it's image or video, they all use HTTP2. For Instagram, the API requests use HTTP2, but for the static content, like image and video, they were still going over HTTP 1.1 connection. So for Facebook app, graph, image, and video, they all go through separate connections. And on the Instagram side, image and video can potentially go through the same connection. On the server side, we just use standard Linux TCP stack. The congestion control we use is version 1 of BBR. So on the internet, there's still roughly about 1% of the user who cannot really have their traffic go through UDP over port 443. And 1% user in Facebook's user base is a very large number. To make sure that when we enable QUIC and HP3 for our users, they can still safely and reliably use the app, we come up with this algorithm to raise the QUIC and TCP connection when we need to open new connection. The idea is very simple. So we open a QUIC connection and we wait 200 milliseconds. After that, we fall back to a TCP connection. And if we have both QUIC and TCP available in our session pool on the client side, we always prefer QUIC connection. So this algorithm clearly has a preference in QUIC over TCP. That's because our data shows as long as QUIC is not blocked, it always performs good or even better than TCP. So with this algorithm ready, we were ready to run real experiment with production traffic. And I will give it back to Matt to talk about congestion control and the flow control.
Thanks. So yeah, so to understand some of the challenges we face next, let's start with some basic definitions of congestion control and flow control. So congestion control is essentially an algorithm used by a sending transport like TCP or QUIC to minimize loss or congestion and maximize something like usually throughput. So our ability to deliver data to the client. Flow control is different. Flow control is essentially a way to limit the amount of data that an application buffers. So if I'm receiving data, I might want to say, oh, I only want to receive 100 kilobytes or 2 megabytes of data. And once you hit that, don't send me any more data until I tell you it's okay. So this is essentially a way to limit the amount of data that a receiving application has to buffer. Next slide. So an interesting thing that we saw with congestion control, and specifically on Instagram, was, if you remember what Yang said, Instagram was using 6 connections to fetch data from the servers. Now, it was not only doing this basically for multiplexing reasons, so that it could have multiple in-flight requests at the same time. But another side effect of this is that for the first request that the app makes, it's able to download quite a lot of data in that first initial flight. And this is because the sending congestion controllers, they're all independent, and they all decide, okay, we're gonna send not too many packets because we don't know how much congestion there might be, so we're gonna send 10. But since there's 6 connections, it's actually the same server will end up sending about 60 packets to the same app. Now, if we go to the next slide, when we changed everything to QUIC, since QUIC has multiplexing on a single connection, we don't necessarily need those 6 connections to achieve multiplexing. However, it ends up being disadvantaged compared to those 6 TCP connections early on, because that same connection is still limited by those 10 packets. So this showed up meaningfully in the metrics when we tried to use QUIC and Instagram, mostly in metrics related to app startup time and media loading. And so how did we decide to fix this? Well, basically, we split the difference. And so we had 1 connection, but we decided, okay, we're not going to go all the way to 60 because that's quite high. But what about 30? 30 is a more reasonable number. And indeed, it's still less impactful to the network than having those 6 connections. But by doing this, we were actually able to completely make up the gap in those metrics with TCP and actually even improve it. So we ended up having the media load times during startup were improved by switching to QUIC with this increase in initial congestion window. Next slide. So I've already mentioned congestion window a couple times, but let's talk about it again a little bit more in detail. So suppose you have a 10 megabit per second link with 100 millisecond RTT, or round trip time. So a round trip time of 100 milliseconds means that the time it takes for a packet to go from one end to the other end and back again is 100 milliseconds. So a question you might ask, and a question that we ask in servers, is how much data do I need to have in flight in order to fully utilize this 10 megabit per second link? And to do this, it's just simple math. You take the link speed, you multiply by the round trip time, and you get something called the bandwidth delay product, or BDP. And the BDP is also a sort of idealized congestion window, which is the amount of data that a server should have sent to maximize the throughput here. Next slide. So why is this relevant? This is relevant because of flow control, because congestion window can essentially be bound by flow control. What I mean by that is that flow control essentially, as we said, limits the amount of data an application is willing to receive. So in TCP and with HTTP2, there's 2 layers of flow control. There's the TCP flow control and there's the HTTP2 flow control. The TCP one is determined by the TCP stack. It shrinks and grows over time, and you don't really mess with it too much usually. The HTTP2 flow control is set by the application very explicitly. And for us, it's usually static in size. So you set it to, say, a static number of like 100 kilobytes, 1 megabyte, 10 megabytes, whatever you want. Now in QUIC, since the stream multiplexing and all of that is built into the transport, there's no separate flow control for like the transport and HTTP. There's just one, and it's controlled by the transport. And similar to the HTTP2 one, we have it set by the application, and it's also static in size. Now, something that we found was that the static limit set by our applications for HTTP2 did not work well for QUIC. So it was set to something like 165 kilobytes. And when we tried to use this with QUIC, we would see a lot of negative metrics. And so to figure out why, we have the next slide. So one way to visualize this is we can go back to that ideal congestion window idea, which is for that 10 megabit per second link, at 100 milliseconds RTT, we want to have ideally 122 kilobytes of data available in order to maximize that throughput. But the flow control, if you remember, limits the sender from sending more than a set amount of data. So if you have the flow control, let's say, set at 100 kilobytes, then the sender has no choice but to respect that, and it's unable to really fully utilize the link. And so like in this case, the flow control is too small. It's 100 kilobytes. It's less than 122 kilobytes. And so all that image and video data, it's kind of constrained by what it could potentially send simply from the flow control. So next slide. So the way that we can fix this is essentially allow the application to have a higher flow control limit. And so in this case, when you set it to something higher, like 2 megabytes, your ideal congestion window is 122 kilobytes. Well, now the congestion window can grow because the server is able to send more data that fits more data onto the wire, which has a higher throughput. And that leads to a better experience for the user as they're able to download things like images and videos much faster. And this is something we had to do for QUIC in order to show improvements over HTTP too. Next slide.
So we covered congestion control, we covered flow control, we talk about how we can safely raise a QUIC connection and a TCP connection so that the user always have a connection to use. If you're a networking person, I hope you find all those topics very relevant to you. As a networking person myself, when I started to work on this project, I was also thinking, those will be the problem I will run into and I will have to solve. And turns out there are also some very surprising application behavior that I actually need to understand to actually make QUIC and HTTP3 worthwhile. The first example here is when we started to enable QUIC and HTTP3 in the Facebook app, we started small. We first only enabled it for the GraphQL, the API requests. And surprisingly, by enabling QUIC for GraphQL, we regressed image and video requests, which was still over HTTP2 and the TCP. We did not touch image and video at all, but somehow they regressed. So how did this happen? After some debugging, what we figure out is the first initial feed loading request, when this was sent out from the application has this heuristic. If it gets the response within 2 seconds, it will try to load fresh feed from the network. But if after 2 seconds, it still has not received the feed loading response, it will actually try to load feed from a local cache. As you can imagine, when we switched to use QUIC for the GraphQL request, because now it is faster, we have more users that's within this 2 seconds limit. But then their TCP, their image and video requests are still over TCP. So the percentage of image and video requests that will be used in a relatively bad network actually increased. So this is why those metrics actually regressed. Once we also enabled QUIC and HTTP3 for image and video, this problem disappeared. Another very surprising app behavior that we had to understand was in the Instagram Android app. We enabled QUIC for video, image, and API requests. For API and video, everything looks very positive. But on the image side, the number was quite mixed. A notable regression is the image queuing time in the app itself. So it turns out in the application, there is a rather complex request queue that has a separate portion for the image. And as QUIC make the video download slightly faster, the video player started to fetch video of higher resolution. So the video response starts to take a larger chunk from the request queue because the request queue also has a response byte limit. And as a result, some image has to wait inside the image queue slightly longer. We solved this problem by tuning the response byte limit in this request queue. So with all those changes that we have mentioned, eventually we were able to deliver a very significant win in both Facebook and Instagram app, especially for video performance. We were able to reduce the mean time between buffering of the video in the video player by 22%, and also a 20% decrease of video stall. We were also able to reduce 8% of the networking errors that the video has to run into. This is the timeline of our project of working on QUIC and HP3 at Facebook. There are many milestones in the past 3 years. One thing very notable is from the beginning, which is early 2017, to the point where our code is able to interop with other implementation. That's slightly beyond half a year. But from there, it took us another 3 years to actually ship this project.
So what are some of the takeaways here? So one thing that I think is really significant is that while QUIC does perform better and QUIC can give you great performance, it's not as simple as turning it on. It's not as simple as implementing it, flipping a switch and turning it on. And this is usually because existing, especially complex applications, can be sort of implicitly tuned or coupled to TCP. And another interesting thing that we saw when we were doing early experiments is that HTTP and transport metrics, so things like latency, number of losses, number of retransmits, things like this will often just show blanket improvement with QUIC. They'll just be like, oh yeah, this all got better. This is all really awesome. But then we look at the application metrics and there'll be regressions. And this can be really confusing and really difficult to reason out. But you often have to do this in order to ensure that you're not just making some numbers better on paper, you're actually improving the experience of those using your applications. But once you do this, put in this effort, QUIC will have a transformative effect on your application performance on the modern internet. Now, in terms of future work, where are we going? So you might have noticed that we didn't mention two probably headline features of QUIC, which are zero-TT connection establishment and connection migration. And these are very important features, but we didn't actually need them to replace TCP with QUIC. And there's a couple of reasons for this. One is that zero-TT essentially improves the experience when you have a new when you need to make a new connection. Well, with our applications, they'd already been highly optimized to reuse connections really aggressively. And so being in a state where you don't have a new connection is relatively rare, and it mostly happens when you're just starting the app up, which is not the majority of the time. It's important, and in fact, we're experimenting with zero-TT right now, but we didn't need it to ship QUIC. Another one is, of course, connection migration, which is this notion that you can seamlessly transition between, say, a Wi-Fi interface and a cellular interface and not interrupt the user's connection. Well, it is really great on paper, but the implementation complexities are significant, both on the client side and the server side, in order to get the most potential out of it. And we just haven't been able to invest all of our time in it yet to ship connection migration, but we do want to do it in the future. In addition to these big headline features, QUIC, because it has inherent extensibility, because it's resistant to ossification, and because we can iterate on it really quickly, gives us a platform for transport and HTTP level experimentation well into the future in a way that was never possible with TCP and HTTP2. Next slide. And that is all we have. Thank you so much.
Thanks a lot for preparing a great talk. I personally always really enjoy those stories of deploying the LoRa, like making big changes, especially in the networking space. Well, that's where I work on as well. And running into this sort of surprises, coming to the space with one sort of expectations and then realizing, oh, things are actually quite a bit more difficult than one expected them to be. So we should have about 15 minutes for the live Q&A. For the attendees, I would encourage you to post your questions into chat. As they come up, we'll hopefully get to most of them during the session. I think the first question that I have, as I was listening to your presentation, you've mentioned the timeline, that it took you quite a bit, like over about 3 years to go through all the steps. What are the main reasons for that taking 3 years? Was it some of the operational challenges? Was it some aspects about quick sanitization or something else?
I would say that it was mostly the fact that it took a while to get to the baselines where the infrastructure supported it. So that took quite a while. Like, it's one thing to interop with, some other implementation and like a one-off. It took a lot longer to make sure that like everything was ready to go and like in the app and like the code was there and like even working. And then the majority of the time though, really after that is we can't just turn stuff on because we want to. We have to make sure it actually improves the experience. Otherwise, it's kind of pointless. So I think most of it was investigating regressions that are caused either by tuning or bugs. It would be what I would say. And Yang, you want to add anything to that?
Yeah, I think I agree with what Matt just said. I think one thing I would add is understanding the networking behavior and the understanding why application is going to see a regression. There is always a gap there. The visibility, the causation, we change this, we change A, and then suddenly system B has some number moved. Sometimes that's not always clear. So figuring that out took surprisingly the amount of time. So.
And can you identify maybe some of the good practices that you follow at Facebook to optimize that process? Because like in my experience, I can totally relate that this is like you nailed it. This is the key of rolling out kind of changes, especially on the kind of transport or like on the infrastructure layer. But at Facebook, like what do you do to make it more optimal and kind of prevent some of the delays or prevent some of the outages issues that would be impacting users?
Yeah, so we had a couple things, which is like first off, when we say like we turned on or shipped QUIC, like this is all gated by basically experimentation frameworks that let us selectively turn it on in the application, so like in the mobile apps, and we can also turn it off, right? So like we can turn it on, we can turn it back off, and then of course we can also turn it on and turn it off at the server side. So like if we found a problem, which did happen, where we'd find like, oh, we shipped a bug, we can still turn it off both on the clients, but really in an emergency we can just totally turn it off entirely. And we really were able to leverage, like Facebook has a lot of this stuff just for general experimentation, because this is how the products are developed, this is how the infrastructure is developed, is to iterate quickly, and there's a lot of tools to help us do that, and we were basically able to integrate into those really easily.
And as you go through those migrations, do you enable things for all the traffic, or do you try to break things down by the functional or by the user sharing or something else? Like I know that in the talk you mentioned that you treat Facebook and Instagram as two different use cases because they operate quite differently. But are there any other segments that you have to make those deployments easier?
Yeah, we would segment like. We would basically have like little groups that would, this group has this on, this group has this on, like, so like with the flow control experimentation, for example, we have like different groups that have the default, a different group that had like another number, and we just run that experiment, and like separately we'd have like, oh, this is the experiment where we're changing the way we map error codes or something, and so like try to test things individually to see like what their individual effect is. Try not to compound the signals too much, so that because like Yang said, like things can have really unexpected, like you turn two things on and like a third thing moves, but only if you turn these two things on. So it's like being able to isolate that is really important.
Great. Yeah, so let's take questions from the chat. So the first one, so QUIC works on top of UDP. So can you elaborate a little bit more on the experience of dealing with UDP being blocked, and how do you generally dealt with it?
Yeah, so basically the flow that Yang showed with the racing, that is the way that we deal with UDP being blocked, which is to say that we always have a TCP fallback in the case that we can detect that a quick handshake is not going to complete. And most of the time when that happens is because UDP is blocked or not functioning for some reason. In terms of its prevalence, it's kind of difficult actually to answer that question, just because it kind of depends on how you frame it. like if you frame it in terms of number of users, if you frame it in terms of like number of networks, number of sessions, like these are all different things. What we can say is that, like, the vast majority of the place, it is not blocked, and it's a lot of this is probably because it's kind of been normalized a bit. Even so, before even we were rolling out QUIC, Google had a proprietary variant of QUIC that also ran UDP on port 443. And so they've already done a lot of groundwork there to get it unblocked generally, but there still are places. But it's usually like you can tell really obviously that's like some network, or like a lot of it's companies, like some companies clearly blocking it with their firewalls. But it's in general not a huge problem, and it's like really less than 1%, no matter how you slice it, of users are going to be impacted by this.
And I think I remember from the Yang's flow that was on the slide that he chose 200 milliseconds as the threshold to fall back to TCP. Why 200 milliseconds? What's so magical about this number?
We actually tried a couple of different numbers. It honestly didn't show too much difference. Like, we tried something slightly longer, something slightly shorter than that. There isn't much difference. Like, once you are let's say, sub 500 millisecond range, there isn't too much scientific behind that either. It's really a experimental result.
And do you save that decision to stay on TCP throughout, like, on local on a device? So every new session, that decision has been made.
I think yes, every new session there is this 200 milliseconds delay, with one exception, which is if your last attempt of using QUIC actually run into an error, we actually does not delay the next time we open a TCP connection.
Yeah. Okay. Yeah, I think the question is there a Java implementation for QUIC at this point?
There's a lot of implementations. If you go to there's the QUIC working group has a GitHub, and there's a list of implementations there, and there's like literally dozens. And I think there's at least 2 or 3 that are Java or something that runs on top of the JVM. But you can there's the nice thing about QUIC is, since it's built on top of UDP, like lots of people have implemented it. There's many more QUIC implementations now than there have ever really been TCP implementations.
And how would you estimate the maturity level of those implementations? Because still it's a relatively new protocol, especially compared like to TCP, etc. And I think you mentioned that during the talk. So being the co-chair of the QUIC working group, like, what's your current take on that?
So I think that there are it varies a lot. We're kind of at the beginning of people really using it outside of, like, Facebook and companies like Google are in sort of a unique position where we often control both sides, with the client and the server, and this gives us an ability to be like, we're going to control these implementations. A lot of people are not in that position. They only have one side, and that makes the iteration time slower. And that means they're going to find bugs and find these other things slower. So I would say that they've done a lot of great work. I would not expect that, like, if you're going to go invest time into QUIC, expect to find problems like that right now, because they're still early days for these implementations, but I'm sure they will mature really rapidly over like the next year or 2.
Okay, yeah, that's great to know. So I think in the presentation you've mentioned some interesting findings that you've had at Facebook of application code making some assumptions about transport behavior. Can you elaborate a little bit more, maybe a couple, like, were there any more stories and learnings from Facebook, or maybe you've seen some other patterns, like in the industry in general, how applications are coupled with TCP?
So one general thing I think is that this multiplexing thing, so like with HTTP2, you have multiplexing, but it goes over that single byte stream, and that kind of makes the multiplexing different than if you have in QUIC when you have these independent byte streams. And so I think a lot of complex applications will see this sort of weird behavior where they have some sort of gating mechanism that they're implicitly relying on, whether it's like we saw it in Instagram with that request queue, we saw it in both apps with the flow control, but some sort of like mechanism to try to limit how much data is being fetched. And these seem common because we've seen them multiple times, and they seem kind of to arise naturally. And I think that when you have these gates, you have to decide on a number, and often, and those numbers, that's where the implicit tuning comes to TCP, which is to say that like somebody iterated on that a few times and they tweaked it, and they arrived at this magic number, and that will potentially be where you need to change stuff, which is, it can be difficult to realize that because you don't realize like, somebody made this change a while ago, but that's where you often need to look. Other things, it's like, it's more like concurrency in general. Like your concurrency limits might be different for like how many requests you can send, things like that. Would be what I would say is just fundamentally different because of how TCP works versus how QUIC works.
So basically, the connection pool on the client, on the server, is making specific assumptions of how the transport layer works, right?
Yeah, pretty much.
Yeah. Cool. I think we have time for one more question, and there were two interesting ones in the chat. So you've talked about the public-facing network interactions and using QUIC for that. How's your position of using QUIC for data center communication, so communication between edge and the origin server?
Yeah, so we had one slight mistake on our slide there, which is corrected in the downloadable slides, which said 50% of edge-to-origin traffic using QUIC. That was specifically for basically when we proxy the API request, 50% of those go over QUIC, and we had that as a test bed. In terms of QUIC for other traffic, it's something that we're working on. It has more challenges in the data center, which is to say that like, because it's implemented in user space, there's obviously performance overheads that come with that, and also the encryption happens a bit differently in QUIC, which happens on a per packet basis, which is less efficient than with TCP, and so these are challenges that we think we can overcome, but they make it difficult for certain use cases. But for some use cases in the data center that aren't like super high throughput, like sub gigabits per second use cases, or use cases where you go from like an edge location out to like another location on the internet, that's a place that we think more immediately could benefit from QUIC for the same reasons that it does benefit QUIC going from the edge to the client. So it's something that we are hoping to explore over like the next year, and we're hoping also to get like the costs down in terms of making QUIC truly usable everywhere where TCP is currently used.
All right, I think we are at the end of the session, and Yang and Matt, thanks again for preparing the presentation. Thanks for providing lots of extra insights during the Q&A. We have about 20 more minutes in the Hangout room and in Zoom, where everyone would have an opportunity to have a little bit more informal conversation, ask questions in person, and then we didn't get to a couple questions in the chat, so that would be a good opportunity for us to keep the discussion there. I'm going to head out there right now. So again, thanks again for the presentation, and see you in the Zoom room.